Good afternoon to everyone. Most of the dignitaries, resource persons, and students have joined online for this inauguration function, either on WebEx or YouTube platform. I welcome you all on behalf of Homi Bhabha National Institute for inauguration functions of the online course on Advanced Materials Chemistry. Today with us, Professor Sandeep Verma, Secretary, Science and Engineering Research Board, Government of India, and Chief Guest of today's function. I welcome you, sir. Professor Verma's presence here is a great moral booster to all the students who are going to participate in this online course and also to HBNI functionaries. I extend warm welcome to Professor P.R. Vasudev Rao, Vice Chancellor, Homi Bhabha National Institute. This course is outcome of his constant encouragement and interest in conducting advanced courses on various topics. I also take this opportunity to thank Professor A.K. Tyagi, the course director of this course. He is senior professor at Homi Bhabha National Institute and associate director, Chemistry Group, Bhabha Atomic Research Center. He formulated the course content and picked up the resource persons very judiciously. I welcome Dr. Anshu Singhal, the course coordinator for the course, for taking responsibility for planning and execution of this program. I am thankful to all resource persons. Dr. Vinita Gupta, she is with us here. Dr. K.C. Barik, Dr. R.K. Singhal, Dr. Dimpar Datta, she is with us here in the Council Hall. Dr. A.K. Chauhan, who agreed to spare the time to deliver the lectures for this course. I welcome them all for this inauguration function. HBNI was established on 3rd June 2005 to provide an academic framework for integrating basic research with technology development. Apart from this, to encourage interdisciplinary research, to nurture environment for attracting high-quality manpower in the science, including the engineering science, to take up a career in nuclear science and technology and related areas. HBNI is fulfilling these visions, and apart from this, HBNI has plans to fulfill its societal obligations by conducting many advanced courses on the various unique topics. This is possible due to expertise available in 10 of its constituent institutes and 1 off-campus centers. We have expertise in almost all the fields in science as well as in engineering and also in medical sciences. Most of our institutes, what I was referring about 10 constituent institutions and 1 off-campus centers, are engaged in fundamental and applied research in basic sciences, mathematics and engineering sciences, as well as medical and health sciences. This course, which is starting from today is the inauguration day. This is the 5th in the series of advanced courses offered by HBNI in last 1 year. And many more are in pipelines. I appeal to the students to write to us if they want HBNI to conduct some unique courses which are not offered by most of the conventional universities. We'll try our level best to meet your expectation from us. I'm quite sure all of you are looking forward in gaining in-depth knowledge in material chemistry from this course. And as you know that I should not say you again because you are now grown up, that this is possible if you give the full attention to the lectures which are going to be conducted online. And online, you have plenty of room for getting disconnected with the lecturers. I request all of you to give full attention. And if you have any doubts, please clear it up with the lecturers. I request all the resource persons, our faculties for this course, to clear the doubts of the student participating in this course. Lastly, I wish all the students who are participating in this course all the best. Thank you all. I request Professor P.R. Vasudharao, VC HBNI, to brief about this course.
Well, Professor Sandeep Verma, chief guest for today's function, Professor J.P. Mittal and other special invitees, Professor Tyagi, director of the course, Dr. Anshu Singhal, coordinator for the course, resource persons, faculty members of HBNI and other institutes, Professor Nayak and my other colleagues at the central office, and my dear students. A very good afternoon to all of you. You will be hearing about the course later from Dr. Anshu Singhal. So I will just share a few of my thoughts on this occasion. Well, we are living in an era where materials are the key to high performance in every gadget or every tool that we use. If you take the most ubiquitous example, the mobile phone, a gadget that practically everyone in the country has. Life is very incomplete without a mobile phone nowadays. You will find that the heart of the mobile phone is materials technology. In fact, mobiles have special materials consisting of many rare elements like gold, yttrium, indium, and so on. The touchscreen of the smartphone is made mainly of indium tin oxide. The rechargeable battery has lithium cobalt oxide. The microcomputer that runs the phone has silicon at its heart. So one can imagine that if man has been successful in producing such gadgets, I would say that it is mainly due to the success in mining these elements, preparing various compounds, their purification and characterization, without which it would have been impossible to realize such gadgets. Because I am not an expert in materials chemistry, when I was asked to share my remarks, I thought I should first do some reading and look up at some hot topics. I tried to see what topics constitute the frontiers of chemistry today. And I found that there is indeed a journal whose name itself is Materials Chemistry Frontiers. And it has an impact factor of 6.78, which is very high. Then I tried to find out what were the hot articles which appeared in this journal in the year 2021, just to understand about what is the latest in materials chemistry. And I came up with a list of very interesting topics on this website, which had some pattern. I'll just read out a few of the topics I read on that web page, which were considered as the hot articles in this journal in the year 2021, that is this year. Ceria doping boosts methylene blue photodegradation in titania nanostructures. That is the title of a paper. Controllable growth of layered nanosheets for high performance water oxidation. Research on metallic chalcogen functionalized monolayer puckered V2CX2 type of compounds with excess sulfur, selenium, or tellurium for lithium ion battery anode materials. Carbon incorporated Fe3O4 nanoflakes as high performance Faraday materials, stencil mask defined Dr. blade printing of organic single crystal arrays for high performance organic field effect transistors, aqueous rechargeable lithium ion battery with long cycle life and overcharge cell protection, and so on. I could see that all these articles were connected in some way with energy, either its generation or its storage or its utilization. So one can easily appreciate the importance of materials chemistry, therefore, in achieving innovations in energy-related technologies. Personally, I am more familiar with nuclear energy, and I know for sure that materials chemistry is in fact at the heart of nuclear technology. If you want to operate nuclear reactors safely and produce nuclear energy economically, the performance boundaries of various components need to be pushed. And whether you are looking at nuclear fuel, a coolant, a moderator, or a structural material, one will find that the chemistry of the material largely decides the performance boundaries. Leaving aside the nuclear technology, we still know very well that the future of our world is going to heavily depend on arriving at sustainable options for energy. There is high emphasis today on green sources of energy that will have minimum impact on the environment, how to reduce our dependence on fossil fuels and increase our utilization of renewable sources of energy, and particularly solar energy. If these efforts have to be successful, we can realize that materials chemistry will be a very important aspect to look into. Considering the need for the limited time available for me, I want to discuss just a few points more. One unique aspect of materials chemistry, the need for control and characterization of composition and impurity levels in materials for various applications. For some applications, we need materials of very high purity, extremely high purity in some cases, like in the case of radiation detectors, where high purity germanium is used. I am told that such a material will have 13.9 purity level, that is 99 point followed by that many nines. Well, it's a question, how do you make such a pure material? There is material chemistry there. What impurities should you focus on? You need to understand the behavior of impurities in the material. How will you characterize when the impurity levels are so low? How will you plan for standards for characterization and certification of the material? These are all very important and very interesting challenges for the materials chemistry specialist. And without the synergic effects of material scientists with a variety of other specializations, it is not possible to realize such material. If high purity material is one side, the other side is material with controlled amount of impurities and defects. This also is required in many cases, especially for improving the performance of the material. For me, the most easy example to give is stainless steel itself, where the addition of controlled amount of carbon is extremely important in deciding its strength. In many other materials as well, like semiconductors, very small quantities of dopants in very carefully controlled levels have to be added to optimize the conductivity. It is well known, for example, that addition of very small concentration of antimony can significantly improve the thermoelectric properties of magnesium silicide. So careful optimization of impurity levels, controlled synthesis, precise, accurate characterization. So these are all elements of materials chemistry which become very, very important for success in utilizing the materials for various applications. The other aspect, apart from the composition and impurity level, interestingly, is stoichiometry. And for that matter, I would say not stoichiometry, non-stoichiometry. It's another important aspect of materials chemistry, which plays a very crucial role in many systems. I will give again an example connected to nuclear energy. In fast reactors, the oxide which is used as fuel has uranium and plutonium, and therefore it's called uranium plutonium mixed oxide. General formula for such an oxide will be uranium, plutonium, O2, MO2. But experience has shown that the stoichiometric mixed oxide is so much oxidizing that it will not be compatible with the stainless steel or with the coolant sodium used in the reactor. Therefore, the fuel used in the reactor has to be substoichiometric. But how much substoichiometric? Again, too much substoichiometry poses other problems. And finally, one sees the kind of recommended value as 1.97 instead of 2, plus minus 0.01. Well, you can see it's a challenge for the materials chemist. He is required to develop reliable methods to measure the oxygen to metal ratio in such compounds with such high degree of precision. What is required is usually plus minus 0.002 to be able to certify the material. I am giving this just as a few examples to illustrate the importance of the specialization of materials chemistry in a variety of domains, and particularly in nuclear science and technology. I am very happy that Professor Tyagi, a renowned specialist in the subject of materials chemistry, has come forward to organize this course. And I convey my thanks also in advance to Dr. Anshu Singhal, who will be coordinating the course and remaining in touch with all the students and faculty. My thanks to all the resource persons who will be delivering the lectures. I am sure that all the participants will find this course very interesting and useful. And I hope that some, if not all, will also take materials chemistry as a subject for their research career. Before I conclude, I also thank Dr. Sandeep Verma for sparing his valuable time to be with us today and to address the participants. So with these few words, I hand over the mic to Professor Tyagi. Anshu Singhal will explain about the course now. Okay.
Respected Chief Guest Professor Verma, VCHBNI Professor Rao, Professor Nayak, Professor Tyagi, distinguished faculty of the course, distinguished dignitaries who have joined from all CIs and OCC, and dear participants. A warm welcome to you all on the inauguration function of the course on Advanced Material Chemistry. Since the time pandemic has struck the whole country, HBNI has been taking great efforts to run its academic process smoothly and has been organizing online courses for the benefit of not only HBNI students, but to a wide variety of students from all across India. The course on online course on Advanced Material Chemistry begins today. So, online course on Advanced Material Chemistry begins today with inauguration happening right now, and classes will continue up to September 29, 2021. The classes will be held every Monday, Wednesday, and Friday from 16:30 hours to 18 hours. The course has been designed by Professor A.K. Tyagi, Senior Professor HBNI and Associate Director Chemistry Group BARC, who has been working in the field of materials for almost 3 decades now. So he is a real specialist. And I will be coordinating the course from HBNI. I recall here the words of Professor Lane, whom we had privilege to listen to just a few days ago on our HBNI Foundation Day, The chemistry has creative power and can create new materials which did not exist before. The materials can have novel properties and can range from day-to-day use to even materials used in sophisticated material used in aerospace engineering and other fields as well. So material chemistry is a very important subdiscipline of chemistry, which studies the chemical nature of materials. It involves 4 primary components: synthesis, like how we are making the materials; the structure, how are they put together, how are atoms, molecules arranged; characterization, how do they behave; and applications, are they good for anything or not. So material chemistry takes you inside the fascinating world of functional materials that have direct technological applications. So it does offers a strong link between basic science and many existing and newly emerging technologies. Now, all these advanced materials or functional materials which we are studying, they are the building blocks of the society. They form the building blocks of the society. So material chemistry has a societal impact as well. So learning the course and applying the knowledge for your research will definitely bring you one step closer to serve the cause of science for society. The target students for the course are PhD scholars in different CIs, OCC of HBNI, as well as in other Indian universities and educational institutes. Also young faculty who are engaged in research in material chemistry or related areas. The course will be completed in 30 lectures of 90 minutes each, and the course carries 6 credits. The course is being taught by the distinguished faculty from BARC who have been working in their subject areas for many years and really experts in their subject areas. The course is divided into 5 parts. The first part, general material chemistry, will give you indication about the basic concepts as well as various synthetic techniques to how to synthesize materials and all, and will be taught by Dr. Vinita Gupta. Then characterization techniques, which will give you an overview of bulk as well as surface techniques, will be taken by Dr. K.C. Barik. Now, the chemical analysis of the material is a very utmost important. So all the major trace and ultra trace analytical techniques will be taught by Dr. R.K. Singhal. Functional materials part 1, which will give you an overview of batteries, magnetic materials, as well as catalytic materials used for heterogeneous catalysis. The lectures will be taken by Dr. Dimple Datta. And functional material part 2, which will give you an overview about photovoltaics, thermoelectric materials, as well as will teach you how we can make devices from the materials which have been synthesized. The lectures will be taken by Dr. Anil K. Chauhan from BRC. Now here are a set of instructions for the participants. Login username and password will be emailed to every participant for logging in at the Anuvidya site, www.anuvidya.in. They have to use the link given at this site after logging in to join the lectures, and the link will be activated before the lecture starts. The participants who are requesting for participation certificates, they need to attend at least 75% of the course lectures. Students who wish to get credits for the course, they need to attend 75% of the lectures, submit the assignments, and appear for the final examination. The lecture and assignments will be uploaded at website www.anuvidya.in for access by all the participants. We have created a dedicated email account, amchbni.gmail@gmail.com. Here at this email, you can submit your feedback, your comments, your suggestions, your queries, as well as all the assignments will have to be submitted to this email ID. The participants can post their queries on chat mode when the lecture is in progress. And when the lecture is in progress, they should keep their audio and video muted. The most important of all participants should mention the code assigned to them by HBNI in chat mode to enable us to register their attendance when the lecture begins. So happy learning to all the participants. With these words, I now invite Professor Tyagi to deliver his lecture on what is materials chemistry.
Thanks, Dr. Singhal. Professor Sandeep Verma, Secretary SCRB, and Chief Guest of today's function, Professor P.R.V. Rao, Honorable Vice Chancellor, HBNI, Professor P.D. Nayak, Dean HBNI, respected Dr. J.P. Mittal, who has joined online, and other dignitaries from DAE and outside DAE who are part of this inaugural function. Last but not the least, the delegates, the participants of this program, for whom we all have assembled here. A very good afternoon to you all. Before I start my presentation, I just want to share a few things with you. What led to origin of this course? As it was mentioned by Professor Nayak some time back, that June 3rd is celebrated as Founders Day, Foundation Day of HBNI. June 3rd, 2020, it so happened, VC HBNI asked me to give a talk, and I gave a talk on rational design of functional materials. After this talk was over, he told me that if possible, why don't we come up with a program, a course, online course on advanced functional materials. So that initial discussion on June 3rd led to this course. And I also recall June 3rd was the day when Mumbai was hit. June 3rd, 2020, to be very precise, was the day when Mumbai was hit by cyclone Amphan. So previous day, myself, VC sir, Dr. Nayak, we had a video call and we decided not to cancel the program and go ahead. So that small discussion led to the course for which we are today going to inaugurate. Please share my PowerPoint slide. First slide. Just give me 1 minute, I have to get okay. So in this half an hour presentation or so, I am going to share some of my thoughts with you on materials chemistry. While doing so, you will realize that I will also give an overview of the course. So I will do this while posing a question, namely, what is materials chemistry? But before I proceed any further, I would like to dedicate this call to late Professor Sri Kumar Banerjee. He was Chancellor of HBNI. He passed away about 2 or 3 weeks ago. He always encouraged us to initiate these kind of unique courses for the benefit of not only HBNI students, but also non-DAE students from across the India, including those from remote areas who do not have access to high quality courses. How important materials have been to humankind, you can see from this slide. You will be surprised to know that prehistoric phases of our civilization are named according to the material used by them. Left to right, if you go, you will see Stone Age, which was there for a couple of millions of years, followed by Bronze Age, Iron Age. Discovery of steel led to what is called as Industrial Age. Silicon, we talk about Information Age, and these days we have got at our disposal tools where we can do atomistic level maneuvering of structures, and that has led to what is called as atom materials. People also knew different physical and chemical processes. Separation, for example, physical processing. Forging was known a couple of 100 years ago. Smelting, turning, fabrication at micro and nano scale. And last one, is, of course, laser manipulation, by which one can fine-tune the structure at local sites. Human beings have been studying materials even before leaving the caves. First metal tool appeared perhaps about 6,000 years ago. In 1991, in Alps, Iceman was discovered, body of Iceman, and he was carrying a copper axe. By this, historians, science historians, I mean to say, they could decipher that copper was known and copper alloys also were known about 6,000 years ago or so. So you see the kind of science, materials chemistry being done by those people, though they were not using this word materials chemistry, but essence was same. Materials that change our life forever. I have compiled some of them. There are many more, of course. Wood, clay, fiber, bronze, iron and steel, glasses, paper, plastic, aluminum, semiconductors. Of course, I have not organized them in the order of their evolution. I have just organized them in some or the other way. So you can see how simple materials like aluminum, wood, paper, glasses have changed our life forever. Why iron is so special? Many people think that iron is so special because iron is strong. And that's why iron tools and iron kitchenware was used by human beings since ages. That's not so correct. Iron is so important element in periodic table because iron undergoes lots of changes in properties just by optimum heating and cooling and hold temperature. So it is this unique ability of iron wherein properties change a lot by heating and cooling made it so important. Otherwise, iron is a ductile and reasonably soft material, if not very soft. So you can see how materials chemistry teaches you the optimum heating and cooling rates. In this course, these things will be taught to you. As I mentioned that I will slowly unravel the course content in this fashion. I will not do in a routine fashion. By giving examples, I am going to unravel the course content. Iron to steel, of course, VC sir has already preempted to some extent this slide. But let me just mention, as I told you some time back, that iron is reasonably ductile. The reason for ductile property of iron is that the array of atoms which are arranged in a given plane, they can slide past one another quite easily. And it is this sliding of array of atoms which makes iron reasonably soft. You can hinder, you can hamper the moment of dislocations of iron by incorporating a small amount of carbon, maximum 1 to 1.5%. And this carbon goes to interstices. Next comes how to make stainless steel. Steel is good. Now it is having some desired strength, but it does not have corrosion resistance. So scientists knew that if you can replace 10 to 15% of iron by chromium, you can make it corrosion resistant. Chromium forms Cr2O3 layer on surface, and that is highly protective of further corrosion. So materials chemistry, the theme of this course, teaches you in a given host material how to select the right guest. Not only that, it also teaches you which site is more appropriate. Is interstitial more appropriate or substitutional site? All these concepts will be taught by the teachers, the faculty members. Some of them are present here. Very simple thing like evolution of memory devices, right from magnetic tape, delay line, hard disk, audio tape, floppy disk, and so on. All these things have come to existence just because of advent of different and more efficient materials. The last part of the slide, you can see transistor density from 1 to 16, 16 to 4500, it goes up. Then it goes to million, famous Moore's law. So it is this ability of materials chemists and physicists which led to a revolution in the field of memory devices. Likewise, tremendous chemistry has gone into rechargeable battery miniaturization. This story began in 1859 by lead acid battery, which incidentally are used even till date, followed by nickel cadmium battery, mobile battery, 1991 onwards. Paper batteries, they are like paper. You can fold them, put them in pocket, you can roll them. Coin cell you all have seen, and this small corner in right side is showing you a photograph of very small battery. These are implantable batteries. They can be implanted to human beings. BRC has developed deep brain simulators, and in these kind of devices, these kind of batteries are used. Here, materials chemistry teaches you which kind of casing should be used. Coin cell is using SS casing, whereas implantable batteries cannot use SS casing. We can discuss these things afterwards. For implantable batteries, one uses titanium casing because titanium is more compatible with body fluids. So materials chemistry teaches you the concepts of compatibility. All these things will be taught to you in this course. Lab on chip, they are the wearable devices which you can wear round the clock. They have ability to pick picoliters of blood, absolutely bloodless, no surgery, no needle, and you can find blood glucose meter. They have got a chip also, SIM card is there, and by just a small press of the button, the blood test report immediately goes to a doctor. Doctor can give you the feedback. All these things are now available in market. All this could be done because of advent of nano sensors. These things also will be taught in this course. How to develop efficient sensors and how to miniaturize them. Major discoveries in last 30 years. I have arranged them in decreasing order of year of Nobel Prize. Lithium-ion battery, molecular machines, blue LEDs. As you know, in white light, we mix red, blue, and green. So main issue was to make blue color. Red and green color adding materials were there in plenty. Graphene, new form of carbon, GMR materials, conducting polymers, full range, high TC oxide superconductors. All these discoveries I have personally witnessed. It so happened I did MSc in 1985, joined BRC Training School in same year, and in 1986 I joined BRC. And you can see in same year I saw the discovery of high TC oxide and so on. And I have myself worked in, if not all, in many of these topics. All these things were not discovered by chemists. Some of them are physicists also. But one thing is common, they all have done tremendous synthesis and characterization. These two also will be covered in the course amply. So there are 2 modules on synthesis and characterization techniques, which you can use to your benefit to discover still better materials in your career. So far, so good. I can see many young students who are in their early 20s. They may ask a question, so far so much has been done. What is left for me now to make a career? Here I may emphasize, whatever has been done till date is only tip of the iceberg. Entire iceberg is waiting for you to explore. You can make a huge career while working on functional materials, hybrids, engineered materials, high-end materials for DAE and ISRO, this kind of applications, defense applications, materials for energy applications, and materials for society. I'll give some examples as I proceed further. Next is materials for sustainable life. Massive career is waiting for you in this particular field of materials. Namely, materials for health sector. One has to worry about disease diagnosis at early stage, nano drug carriers, new small drug molecules. In energy sector, one has to make efficient materials for energy harvesting, storage, transportation, biofuels. And in environment sector, one has to talk these days on reduction in carbon credit, nano pesticides, conversion of polymers to monomers. Polymer is a big menace. So can you make catalyst which can degrade polymers into monomer, which was used to begin with? All these things are waiting for your generation to explore. I will spend some time on all these 3 aspects of materials for sustainable life. In case of energy challenges, one has to develop processes for recovery of valuables. Lithium, for example, is very scantily available, that too in a couple of countries. It is called as ABC countries, Argentina, Bolivia, and Chile. They can boast of having more than 50% lithium. So this uneven abundance of lithium also can pose a problem. So we have to develop materials chemistry processes for recovery of lithium. Just one example I am giving you. One has to make efficient electronics and lighting materials. One has to develop protocols for CO2 sequestration, petrochemistry, chemistry, feedstock, etc. Likewise, in nuclear, of course, we are developing materials to be used under extreme conditions. Nuclear-based chemistry, a lot of work has been done. A lot more is waiting for you to do. In case of renewable energies, hydrogen technology, now Government of India is giving a lot of emphasis. So we have to make materials for hydrogen generation, hydrogen storage, hydrogen transportation, batteries, fuel cells, syn fuel, biomass. Solar energy harvesting is another very interesting area wherein a lot of work can be done. This course is designed to teach you fine aspects of many of these things which I have compiled in this slide. Healthcare, in BRC we work a lot on radioprotectors, nutraceuticals, curcumin. Curcumin is active component of turmeric, haldi. Now suddenly after pandemic, whole world has woke up to Indian medicinal plant. Turmeric is one of them. Problem is that they are not having high bioavailability. What kind of materials chemistry can be done to enhance the bioavailability of these kind of important constituents of Indian medicinal plant? Synthetic chemistry and materials chemistry go hand in hand. They are almost like two sides of same coin. One has to make new methods of synthesis of new drugs, deuterated drugs, magnetic hyperthermia, photothermal therapy, and a new concept which is emerging very rapidly is boron neutron capture therapy. Novel drug delivery systems have to be developed, like based on gold, Fe3O4, silica. All these three are biocompatible, liposomal based delivery agents, micelles, hydrogels, and for diagnosis these days a lot of work is done on extracellular acidity analyzer, quadruplex sensors, SPR sensors, and so on. So all these things are there. Some of them will be covered by our faculty members. In case of environment, one has to develop synthesis protocols, to develop sensors for finding persistent organic pollutants in soil. One has to make new analytical monitoring systems, sorption of heavy metal and dyes. Agro-based sorbents have got functional groups. They can be used for remediation of soil. Chlorine dioxide releasing polymer and degradation methods and so on. A lot is there in which definitely you can work a lot on materials chemistry. Now, Dr. Anshu Singhal mentioned the term functional materials, and there are two modules, module 1, module 2. Many times I have seen young students asking this question, what is this term we have never heard? Functional material. So I thought one slide just to tell you what exactly we mean by this term. In this table, you have seen that I have arranged 5 different compounds. Tin oxide is semiconductor, iterothoria is an insulator, calixurin is an organic compound, silverite rhodamine 6G is hybrid material, and conducting polymer is organic compound. 5 different compounds who have nothing in common. Their bonding, origin, structure, properties, everything is different. Still I have put them in same table. It is because all 5 of them are used to make sensors. They are called as sensor materials. They are used to make sensor for toxic gases, sensor for water in molten sodium, sensor for cesium-137 in nuclear waste, sensor for lead-2+ in potable water, and sensor for progesterone antibodies. So these 5 different compounds have got one thing in common, that they are sensor materials. So this is the new way of classification of material, which is based on functionality. I will show one more example, how to convert an ordinary solid into an excellent functional material. Calcium titanate has no property. You replace calcium by barium, it becomes barium titanate. It becomes an excellent ferroelectric material. Zirconia, you introduce yttria, you get yttria stabilized zirconia, which is an excellent ionic conductor. TiO2, you incorporate iron and tantalum, you get FeTiTiO6, which is an excellent giant dielectric constant material. In LaMNO3, you replace part of lanthanum by divalent strontium, you get a compound which shows GMR property and mixed ionic electronic conductivity. Iron to steel I have discussed at length. So the strategy to convert an ordinary solid into a functional material will be taught in this course. Barium titanate is so important because you introduce distortion. Yttria stabilized zirconia, you introduce defects. Professor Vasudev sir mentioned about role of defects. So defects are very important. One good example I have taken from non-nuclear application. FeTiTaO6 is such a wonderful material because of disorder. So optimum degree of distortion, defect, disorder made transformation of ordinary solids into extraordinary functional materials. All these things will be taught, as I mentioned some time back. So one can make functional materials by playing with the structure, by playing with thermodynamics, by introducing defects. It is called as defects engineering, hybrid approach. So all these things are there. To some extent, our colleagues, our faculty members will be teaching you. I have chosen one example just to highlight the role of structure in functionality. Alumina Al2O3 commonly has got two forms: alpha Al2O3 corundum structure, gamma Fe2O3 spinel structure. Alpha Al2O3 is used to make laser host. Ruby laser is using alpha Al2O3, not gamma Al2O3. Whereas in case of catalysis, you use gamma Al2O3 as host, as support. You don't use alpha Al2O3. So same compound chemically has got two different applications. Why it is so? You look at the structure of Al2O3 in alpha form. It has got regular AlO6 octahedra. It has got one type of octahedra. It is called as crystallographically singular position. So when you incorporate chromium to make ruby laser, the line width of ruby laser is very narrow because there is no broadening because of different types of polyhedra present in the structure. Whereas gamma Al2O3 has got two types of polyhedra, AlO4 tetrahedra, AlO6 octahedra. And look at the formula. It is Al2O3 only, but I have written crystallographically. This formula has got, you will see at a glance, one cationic vacancy. It also has got one anionic vacancy. So this presence of vacancies in gamma Al2O3 makes it very active material and enabling it to act as a very good host or very good support for performing catalytic reactions. So you see how crystallographic structure of same compound for two different applications plays very important role. These things also will be covered in the course. We have to work in a rational fashion. So after learning the concept of the structure, namely the optimum arrangement of atoms, bond length, degree of order, disorder, defect, distortion, you have to couple nano attributes. You have to couple size and shape, morphology, microstructure, surface area, energy, etc., and porosity. So the best way is to work at the intersect of two different approaches. So these concepts also will be covered in the course. If you do so, if you have best of both, you can have incredibly improved functionalities like catalysis, sorption, ion exchange, redox behavior, magnetism, mechanical strength, reactivity, etc. Synthesis of materials, I think there will be at least 2 lectures on this. Our colleagues will be teaching you ceramic methods, soft chemical methods. They will also teach high pressure synthesis, and I have requested them to cover some processing also. They will teach you how to make thin films by chemical methods like inkjet printing, screen printing, spin coating, etc. All these things will be covered to the participants of this course. Now, another thing which is very important part of this course is characterization of materials. When I say that a given material needs to be thoroughly characterized, what does it mean? It means you have to find its composition very precisely. You have to elucidate the structure. You have to find the microstructure, and you also have to find local structure and speciation, surface characterization, and you have to find the purity. Which is told about 13N purity kind of materials. For certain applications, I may re-emphasize, it is not sufficient to mention purity alone. You also have to report the impurity profile. 2 examples are nuclear and pharmaceuticals. In both the cases, it is not sufficient to say that my material is 99.99% pure. You also have to report what is 0.01% impurity. Very important. So this particular module of the course will also give enough emphasis on analysis of not only purity, they will also teach you how to assay the impurity profile. All these things I am sure you will find useful as the course proceeds further. Different techniques used for characterization of material can be classified into 4 or 5 wide categories. Diffraction, we have XRD, neutron diffraction, electron diffraction. You can also have one more category, microscopic. You will have SEM, TEM, HRTEM, SPS, IBA, AES, spectroscopy, like NMR, NQR, IR, Raman, EPR, UV visible, Mossbauer, and they are techniques which are used for compositional characterization, as I have listed in the right column, EPMA, XRF, NA, MS. Here I may say that it may not be possible to cover all techniques. This itself needs a separate course, and definitely we will try to come up with one more course on this. When I give talk in person, I ask questions. One question I want to ask you, and please try to answer either sending mail to the journal email or to me directly. What is the most important difference between diffraction techniques and spectroscopic techniques? This question number 1, which I am going to pose to you, and please do reply to me. My email address I will share with you once again. Otherwise, definitely you can ask your teachers also. I move forward. I have told the faculty members to make enough attention on concepts. For example, we talk about X-ray-based techniques, or we talk about electron-based techniques. I have requested them to teach you first and foremost what is the mechanism of interaction of this probe. In this case, probe is X-ray. So X-ray can be used for X-ray diffraction, XRD, the bottommost left box. You can also use X-ray for XPS or AES. So physics is different. The physics behind XRD and the physics behind XPS and AES is altogether different. That's why question number 2 comes to you. Why we use copper K alpha for XRD, and why we use magnesium or aluminum K alpha for XPS? Why not other way around? Why not we do XPS by copper K alpha or XRD by aluminum K alpha? This question is second question of my talk. Please discuss with me, or otherwise ask your teachers also. All these concepts our learned faculty members will definitely share with you. 2 examples, and then I will try to conclude my talk. 2 simple concepts of materials chemistry which have been adopted at industrial scale. You can see the kind of impact which these concepts can make. Right side is the structure of fluorite, MO2. Left side is the structure of perovskite, AbO3. Perovskite structure can accommodate anion, cannot accommodate anion excess. You cannot make AbO3 plus X, but you can make anion deficient. You can make AbO3 minus X. Whereas fluoride, you can make both. You can make UO2 plus minus X. Sometime back, Vishisab was mentioning about all these things. So, one question comes, third question comes, why perovskites behave like this? Why fluorides can have both anion excess and anion deficient? We'll discuss these things at length. But how this concept is used at industrial scale, I show you one example. Of course, FeTiTiO3 is not perovskite, it is corundum structure. It is AbO3, but it is corundum structure. Here comes my third question. Despite the fact, third or fourth probably, despite the fact that FeTiO3 is AbO3, why it does not adopt perovskite structure, why it adopts corundum structure? Please discuss with me or with your teachers. In this course, I think this kind of thing I would overemphasize as course director. We should have interactive discussion on various concepts. It should not be just a course where we complete the entire syllabus. So teachers will take enough precautions, but a lot is expected from your side. So coming back to this industrial application, corundum structure is hexagonal close-packed lattice of oxide ions. How perovskite cannot accommodate oxygen excess, corundum structure also cannot accommodate oxygen excess. So FeTiO3, when you heat in air, it wants to become FeTiO3 plus X, and which is not allowed. So it shows a phase separation to FeTiO3 and TiO2. So from ilmenite ore, rutile is obtained by this simple oxidation process. So concept of materials chemistry, concept of defect chemistry is used at industrial scale. In DAE, we dissolve spent fuel. Basically, it is UO2. So first you do oxidation and then do dissolution. It is called as oxidative dissolution. So when you oxidize UO2 to U3O8, uranium cubic polyhedra gets transformed to pentagonal bipyramid. And in this process, you reduce the lattice energy considerably and dissolution is facilitated. So again, the concept of defects, etc. are used at hundreds of tons scale, industrial scale. So please be very attentive to these concepts when this course proceeds further. Solid state chemistry under high pressure, I won't spend much time because now I'll have to conclude my talk. This also, a colleague of us will teach you how to make compounds under the application of high pressure and what is expected by this unique method. Compositional characterization, this course is unique because in this course, our faculty member will teach you how to characterize a material right from 100% level to 1%, microgram, sub-microgram, nanogram, picogram, femtogram. And at the end, how to characterize at single atom level. Laser assisted, laser ablation, mass spectrometry, etc. will be taught, and AMS. All these things, in nutshell, one entire module of the course, I am showing in one slide. Materials in DAE, it was mentioned by VC sir also. DAE and materials, I can take liberty and say they are almost like synonymous. The materials, wide range of materials used in DAE can be classified in more than one ways. Left uppermost box is material type. In DAE, we use oxides, fluorides, nitrides, silicide, metals, intermetallics, alloys, carbon-based materials, polymers, organic compounds. Materials properties. We want materials to be highly dense, to be highly porous. You see the extremes. Highly dense to highly porous. Nano, soft, ultra hard, inert, highly reactive, luminescent, transparent. And we also want materials for radiation shielding applications. Based on functionalities, we need materials to be used as adsorbent, ion exchanger, sensor, detectors, catalyst, oxidant, reductant, defective solids we have discussed at length, semiconductors, scintillators, composites, multi-layers. In terms of application, in DAE we use materials under extreme conditions. High temperature, high pressure, high radiation, highly corrosive environment, high ionic strength liquids, highly abrasive environment, high electric and magnetic field. You see the kind of materials chemistry is required to develop materials for future. So those participants who are from DAE, nearly half of them are from DAE, maybe 60%. You can imagine the kind of materials chemistry will be taught to you in this course and the kind of materials chemistry which is waiting for you to make huge career. Well, materials for future, one can work on hybrids, and in coming years we have to make hybrids beyond simple organic inorganic. One has to make hybrids of living and non-living bodies. One has to make materials which are environmentally benign because we have to worry about disposal after life. One has to think of recyclability, green processes, metamaterials. This is a new term incidentally. Metamaterials are the materials which have got properties which conventional understanding of the physics does not support at all. So you have to think out of box. Metastable materials, materials consisting of earth-abundant materials, earth-abundant elements. You have to use more of silicon, zirconium, aluminum, etc. Biomaterials, including self-healing materials, materials for environmental remediation, etc. So, materials chemistry is a branch of chemistry which empowers you with concepts of chemical bonding coupled with concepts of crystallographic structure. This branch of chemistry teaches you how to fine tailor radius ratio, counter-ion polarizability, polyhedral packing, coordination number, bond distance and bond angles optimization. All these things will be taught in this course. This subject, this branch of chemistry also teaches you optimization of disorder, distortion, defects. These 3 Ds are not as dreadful as they look to be. In fact, they are responsible for many incredible properties. So not to worry about these things you have to optimally introduce. Innovative yet simple synthesis protocols need to be developed, and you have to think, young friends, beyond thermodynamics and much beyond the concepts of phase diagrams. So this is the course content. I won't spend much time. You all have got soft copy of this. Different modules are listed here. Dr. Anshu Singhal and I will discuss with you. Some books to share with you. We published a couple of books. First one is Materials Characterization Techniques. Second one is Functional Materials. These 2 books could be useful to you. And third one is Materials Under Extreme Conditions. This book may not be very useful to you for this course. And I am, of course, with heavy heart, I again remember Dr. Srikumar Banerjee. With him, I did all 3 books under his guidance and under his leadership. 3 more books are going to be published in next 2 or 3 months. Right now, we are at proof reading stage. These books will be very useful to you. The title is Handbook on Synthesis Strategies for Advanced Materials. I think they are directly relevant to your course. Volume 1 is on techniques and fundamentals. Volume 2 is on processing and functionalization of materials. Volume 3 is on materials-specific synthesis strategies. All 3 volumes put together, this will be about 2,000 plus pages kind of treatise on materials chemistry. Here are the faculty members. Dr. Singhal, I'm not going to read their biodata. They all are well-known people in the field. Dr. R.K. Singhal, Dr. Anil Chauhan, Dr. Dimple Datta is sitting here. Dr. Vinita Grover Gupta is also sitting here. Dr. Barik also has joined us. So you will be interacting more with them. I must conclude my talk by conveying my sincere thanks to respected Professor P.R. Vasudeva Rao, VC SPNI, for kindly prompting me to initiate this course. Professor P.D. Nayak, who has been guiding all throughout. Dr. Anshu Singhal, ably coordinating the course. All course faculty members, I have mentioned their names some time back. And last but not the least, I need to thank all of you for showing faith in this course. So I am pretty sure it will be useful to you all. You will definitely get benefited out of this course. And in acknowledgement slide, it is uncommon to show email address, but I have done that. So please note down my email address so that you can directly be in touch with me. If you want any mid-course correction, if suppose you feel something is not going on the way it should have as per your expectation, you may write directly to me also. And if these 4 questions, if you want answer from me, we can have discussion 1-to-1, or you can discuss with your teachers also. With this, I conclude my talk. Thanks to you all. Now, the much awaited time has come, and that is a lecture from Professor Sandeep Verma. Professor Sandeep Verma, just to introduce you very informally, he is a very good friend of mine from IIT Kanpur. Now also he continues to be in IIT Kanpur, of course. He took over the huge responsibility of Secretary of SERB. He is responsible for promoting science and engineering in the entire country. He is a very well-established scientist in the field of materials chemistry and chemistry in general. He is a winner of a large number of prestigious awards. Notable among them is Shanti Shuru Bhatnagar Prize. He is also a fellow of all the 4 or 5 science engineering academies in this country. Many more awards are there to his credit. With these few words of introduction, may I request Professor Verma to kindly give his address.
Thank you very much, Professor Tyagi. I must thank you for this invitation. It's so kind of you to have me here, and I'm truly pleased. So before I start my lecture, I would like to thank Honorable Vice Chancellor, Professor Rao, Dean Professor Nayak, and most respected Professor Mittal, who I have had pleasure of interacting. He has been a guiding light throughout my career, that he is present. And it's certainly a very delightful evening for me to be interacting with all of you, and also the course students who are going to be taking this advanced materials chemistry course. And as the stage has been set very nicely by the Vice Chancellor and Professor Tyagi, that how materials have been driving the growth of science and technology, how materials are important in diverse areas of our progress. With that setting up of stage, what I have decided today is to touch upon only two specific areas which are really being highlighted at a Department of Science and Technology as well as Science and Engineering Research Board. And I would like to take students and all of you through the path of a little philosophical as well as, sort of opening up of horizons type of presentation, where I hope I will be able to tell us that what are the gap areas in our understanding, where we have to ramp up our efforts, and where we definitely need more material science, more innovation in material science and technology to align with national missions, and also bring our efforts in synchronization with whatever else is going around in these two areas. So with these few words, I would attempt to share my slides because that is really important. Let me see, and you please tell me if you're able to see the slide. Professor
Yes, we
Tyagi, are
to
you
see.
able to see my slide?
Yes, Professor Verma, we are able to see.
Thank you. So when I was asked to present in this materials chemistry course, I thought that I'll bring in a bit of our new R&D initiatives that have come around from SERB and DST, which have their connections to material science and technology. So with these words, and as it has already been, I have been already introduced, I am at Science and Engineering Research Board at DST, with continued affiliation to my parent organization, where at Indian Institute of Technology, Kanpur. So the first topic I would like to talk to you about is energy transformation and storage. And as you would understand, and a lot of work that you are already aware of, this brilliant work that is being done with the help of our atomic energy institutions, a lot of work is going on in energy transformation and storage. And as you would know, at some point of time, we really do rely on having new materials, which we can produce on our own, where we have the capacity to upscale this synthesis, not just synthesis, but upscale the manufacture, and then use that manufactured product, manufactured material product, to integrate it with devices so that they can not only be transforming energy, but they would store energy and release energy on need basis. So the first topic I would like to touch upon is energy transformation and storage, and just a bit of part of what could be a very large ambit of energy transformation. So I would like to start with a more philosophical thought of what is called as energy trilemma. So energy trilemma is, it's like dilemma, but you have three vertices where you are looking at three very distinct verticals of energy security, which relates to our capacity to, I'll just take the laser pointer, where we are looking at our capacity to make energy demands. We are also looking at energy equity, because not only the energy requirement resides with more people who can afford it, but people who are in the lower category or even at the below poverty line, they also require access to energy. So that energy equity aspect is equally important. And finally, when you are trying to upscale your energy security, when you are trying to look at energy equity, are you able to adhere to environmental sustainability? That forms the third vertex, and that forms the energy trilemma that you see here, where we are moving in an unprecedented transition from carbon intensive fossil fuels and moving all the way to the other end of the spectrum, where we would like to rely on low carbon energy sources, where we can, sort of mitigate climate change, and yet by doing so bring in or make sure that economic prosperity remains viable. if you look at the per capita energy consumption, that shows you where we are at the moment. So, I would not go through the numbers. It is not important. But what I'm trying to show here is that you start with industrialized countries, developed nations, to developing nations, to underdeveloped nations. Bottom line is everybody requires energy, and energy requirement not only depends on the devices that we use or the cars that we drive, but it is also important that we live a normal, healthy, and happy life. It could just be a running of a fan. For some, it could be running of their Humvee, for their sports utility vehicle. Everything requires energy. So that equity, that per capita consumption, if you look at Indian subcontinent in particular, and I'm pretty sorry actually that I have to use this transparency with our map not being shown in the right way, but right now that's the best I could do with this particular slide, where we can accurately present the per capita energy consumption data. So I request all of you to pardon me for that, right? So looking at this, what is amply clear to us is that if we are going from this color all the way to a color where the per capita consumption is going to rise, we have to look at the transition of our conventional sources of energy to renewable sources of energy, or the sources of energy that require or that would afford less carbon footprint. Now, what could be a good way to look at it, or what could be a good way to generate renewables is shown here. So you look at the total energy consumption all the way from 2008 to 2018, and what you find is that slowly but steadily, the share of renewables is increasing in the overall, or the net power required or net energy required by us over this particular decade that we are looking at. So what it means is that we are moving towards a future. We are moving towards a future that is going to be green. We have been, some of you may have heard about the new national mission that is going to be launched about green hydrogen. We have a national mission on electromobility, electric vehicles. So all that is going to come under the ambit or umbrella of renewables, and that share is steadily rising over this decade. So we can imagine, as the generations progress, as we move more towards future, as the materials that would be able to not only generate energy, transform energy, store energy, distribute, or when these technologies become viable, or when these technologies become less expensive, we can think of moving towards a new paradigm of energy transformation, generation, and utilization. So for this, I don't have to mention to this set of participants that you have to realize that eventually materials are going to play an extremely important role when we go toward such kind of scenario. So one definite advantage what India and other countries have is that we have good amount of sunshine. So if you look at the solar map of India, which is shown here, we have the potential, or at least half of the country has potential of enormous sunshine, and having that sunshine converted to solar power. So without going through the numbers, you can read the number yourself. What I mean to say present here is that if we are able to play our cards right, if we are able to develop the technology in the right way possible, and if we can locate our farms, solar farms, in the right locations within country, then these viable location of solar farms and smaller installations that could be integrated into the grid when they are producing energy, when they are generating energy. I mean, the storage is really a bit of a problem, but if you are directly going to feed this energy into our distribution network, we should be able to contribute quite a bit, a substantial amount of energy to the grid. And what is being heralded for future is that at the moment we have a installed capacity of 90 gigawatt, but we are looking at about 175 gigawatt by 2022, by next year, to harness solar energy, to harness the kind of free, clean energy that hits our planet, that hits Earth, hits India, and how we can transform this energy for our benefit. So if you look at the solar photovoltaic growth, India accelerated. We have done reasonably well. We are doing quite, I mean, we are taking good strides. If you look at this brown section in the chart that is shown here, we are slowly catching up. We are slowly but steadily catching up. And this overall growth of solar photovoltaics is definitely dependent on what we can do with our materials and how well we can develop materials to harness the solar power. And some of you would know that we are working in this direction, and there is an international solar alliance that was put together with our honorable Prime Minister. It's an international intergovernmental alliance of 121 solar resource rich countries who have come together and who are located between the tropics of Cancer and Capricorn. And this alliance has promised themselves that we will up the ante, we will go full steam and create potential, create R&D possibilities that is going to upscale this chart, and at some point of time, we will become reliant on solar power to move forward in the direction with the help of material research, with the help of materials being from chemistry to synthesis, to scale up to product. So this whole pipeline is going to be populated at some point of time through dedicated research, and we are going to get to the desired point in time where we would like to get in terms of the amount of energy being generated by solar power. So what are we doing? What is DST doing? What is SERB doing in this part of the research is that we have been supporting upstream end of the research, and we are trying to sort of bring parity and nuance parity when we look at the current industry trends. So the research being done in the lab is going to pair up with the research that is being pursued by industry, and that pairing up of industry trend vis-a-vis what can be done in academic laboratory is the sort of very important aspect of our support. India-centric innovations are important because innovations can happen in other countries, but what actually we require, where is our gap areas if we want to become Atmanirbhar? And I'm sure all of us remember the clarion call by our honorable Prime Minister of being Atmanirbhar, self-reliant. So when you want to become self-reliant, you are looking at India-centric innovation, and that is where we would eventually like to bring in the academics and industry. We forge collaboration. We look at how well our research has translated in the sense of exponential technology. So we also have to develop critical mass of researchers. So in any given area, you cannot really work with 20, 30, 40 people. You have to have a critical mass that can dedicatedly, with a single focus, work in the area so that the requirements of research and development can be met in our clean energy program. So the professional help, the professional research is going to be needed, and that can only be created by having the critical mass of researchers. So we are supporting multi-institutional network research projects where more than one institution can come together, more than one expertise can be brought on the table, and this cross-cutting of expertise, intermingling of our thoughts is essentially going to bring in the right kind of devices, the right kind of global benchmarks, including international collaboration. So this whole ambit of clean energy initiative supported by DST touches upon these 4 bullet points which I have highlighted. Incidentally, although it is slightly away from energy, what DST has also been doing is that we are trying to incite people that can you come up with viable solutions? Can you come up with viable solutions for global cooling? And for this, a whole lot of industries came together with DST, and under mission innovation with the help of the launch, which was done by Honorable Minister of Science and Technology, Dr. Harshvardhanji, this call was launched. And the bottom line there was that can there be a cooling technology which can prevent hundreds of gigatons of carbon dioxide equivalent emissions that come out of various places, and how can you mitigate 0.5, only 0.5 degrees centigrade warming by 2100? It may appear a small number, but it is a huge challenge. And when we make such kind of calls, when we make such kind of international competitions of global cooling competition, that is where the innovation, that is where the youth of tomorrow are going to bring in innovation, are going to bring in new ideas, and that is where your heart should be. So classroom teaching, lectures are good, but at some point of time, maybe 5% of your time, I would request Professor Tyagi should also be reserved for blue sky ideas. Let the ideas come from youngsters. Let the problems be framed by DAE or by HBNI. Let them answer with their innovative solutions, and let us see if they can bring up some new ideas, some excellent ideas, which can be part of the deliverable of this particular advanced chemistry or advanced materials chemistry course. What we have been doing, SERB, what we have just recently made a call. We have made a big call on energy transformation and storage. And within energy transformation and storage, I wish to tell Professor Tyagi, Vice Chancellor Sir, and Dean, and other faculty members that we are looking at 3 different verticals. The first vertical is we are looking at utility scale batteries, transparent photovoltaic. So for example, if you think of an agriculture field, right? So if you were to use that agriculture field to harness solar power, if you were to put opaque photovoltaics, you would not get sunshine, and the land which is underneath that solar panels is not going to be cultivatable. You cannot cultivate anything underneath. Is it possible for us to have large scale areas that could be dotted with transparent photovoltaics, with microgrids, and putting all of them together? Can you bring them, can you connect them to microgrids and other installations that can distribute the power properly? We are also looking at thermoelectric materials and devices, and we are looking at international consortia through Mission Innovation that can feed into our research calls. And we have been looking at Vajra as one of those key verticals of SERB, where foreign collaborators are welcomed in India, in institutions, in universities, and SERB pays them, honoraria to come together and work with you as an adjunct professor. So if HBNI and such institution, if you qualify the call, you are more than welcome to work with us and look at this Vajra, Sir Vajra call and the possibility that ensues. And I'm very happy to tell you that one of our funded research coming out of JNCSR, which is from the research group of Kanishka Vishwas, it was published recently in Science magazine, where they talked about high thermoelectric performance of this particular molecule or by this particular compound that you show on this that is shown on the screen. So while you talk about materials chemistry, while you talk about interesting molecular and physical properties of such materials, be on the lookout that such materials hold enormous promise, and they can not only fetch you good knowledge, but they can also fetch you excellent research publications. SERB support for energy research or energy related material research is also happening through a variety of other programs. One is Imprint India, where we are supporting energy security. We are supporting advanced materials as 2 key verticals where one could possibly go through and create opportunities for R&D support. And Serve Supra, you please have a look out for Serve Supra. It is an excellent program where we are supporting high-risk projects where you have even 50% chance of failure. Now, a new paradigm has set in SERB and DST that we are not afraid of failures. What we want is your best shot. What we want is your best effort with a great idea. If you fail, that's perfectly fine. Some new knowledge definitely will be generated. And I'll be touching upon this exponential technology in a minute. And with this, let me move on to other important aspect of R&D initiatives that has come out of SERB DST, which relates to water, climate, and geohazards. They may not be related directly to materials chemistry, but the materials we use, the emissions that we create, or the carbon black, for example, the material carbon black, when it is exposed in the environment, it leads to glacier melting. So there are collateral damages coming from materials that are being indiscriminately used by us. So water, climate, and geohazard has some kind of connotation attached to materials chemistry. And let me tell you what we have done or what we mean by it, that the first focus of DST SERB is on water research. So any material, any possibility of new ideas which can bring in new innovation or breakthroughs in water and sanitation, which also happens to be the sustainable development goal number 6 of United Nations. So we are looking at the protection and restoration of water related ecosystems, and it requires quite a number of players. Quite a number of players are required, are being pulled in For example, mountains, we talk about forests, we talk about wetlands, rivers, aquifers. All these things are set together, and here are the details of what is SDG 6.1, safe drinking water. How can materials be used to create or to bring in safe water? And I don't have to give you numbers to this crowd or to this participant crowd, is that we have a very insignificant percentage that is fresh water. So we have to preserve water for the preservation of humanity. And that is the reason SDG number 6 is so important. Safe drinking water, water-related ecosystem, sanitation, hygiene, water resources management, quality, efficiency, all put together. We are looking at expanding international collaboration, cooperation, and capacity building in this particular area. And what we have been able to do is going to be seen here. So the first cooperation that we have been able to bring out is between DST, Intel, and Indo-US Science and Technology Forum, where we have been looking at intelligent sensors. So these pebble-like sensors, if you were to distribute it in water, if they are going to connect through cloud, so your Internet of Things are going to be used, or the protocols of Internet of Things could be used, and these sensors can keep on sending, sort of details of the purity of water to a central station. And these pebble-shaped sensors, which are powered by solar wind, by sunlight, wind, or flowing water, they use these energized pebbles to detect the contamination in water, and they send out the details to a real-time server where the details are collected, and the details could be connected through cloud to a researcher, say, sitting in Bombay, and they could be reading what is going on in Haridwar in terms of water purity, or what is going on in Varanasi or Patna in terms of water purity and and the amount of heavy metals or nutrients or dissolved oxygen, whatever else you can think of. So such kind of pebbles can be used, and this award has already been made, and one can expect more such calls coming in the future. So this again is a very interesting concept, where you would use the materials that are going to be used as pebbles, and then you strew it around in aquifers or water stream to get the real-time data. I'm going to talk to you about two technologies that have come from DST support. The first one is from IIT Kanpur, and it is called as Padmavati. So this torch-like thing is Padmavati, and you have to just put few drops of water, and the cross section is shown here. If you can follow the pointer here. So you have battery, you have Bluetooth and Wi-Fi to send the signals of water purity. You have water sample and the test strip, which has the material that is going to detect the contamination, that is going to detect essential water parameters, and that is going to be read by this test strip. It is going to be detected, analyzed, quantified, and eventually this Wi-Fi is going to signal it back to the base station where the data is going to be collected. So there is smartphone connectivity, there is multi-parametric testing. Instant testing means you take only 2 minutes. Only 2 minutes are needed to test a drop of water. It is eco-friendly, and the size and shape is such, I don't have to tell you, you can carry it around anywhere. So this is the innovation that has come out of the support that is being provided by us, and it's a technology that's already been translated, and it's going to be sold at some point of time. Technology 2 is coming from IIT Madras, and this is, some of you may have seen, it is a DST-supported material-based system, a novel material-based system, Amrit, which is which is a boon for smaller communities. So you can have such kind of, such a shaped gadget, if you will, and a tap that is going to give you pure water. And the material which resides inside is based on nanoscale iron oxyhydroxide chitosan composite, which removes arsenic and other heavy metals. And it is a mature product. It is a technology that is being commercialized and being sold in villages. And that is how you bring in innovation to the doorstep of common people. So the doorstep of humanity, getting the innovation that you and I do in research laboratories. This is how we have to target. We have to reach at such places, right? And final few slides. So we have already come out with a slide with a call where we are going to look at projects or proposals coming in artificial intelligence and machine learning in Earth systems modeling. That how the connection of weather, ocean, water, the physical climate, the gases, chemistry, all of it is going to be. Can you hear me?
Yes, sir, we can hear you.
All right. Okay. So we are going to bring in such kind of intertwining of various parameters that can be blended in for our artificial intelligence and machine learning platforms. And this call is already out, and we are going to model it, or we are asking our investigators to model how to predict climate extremities, how to model climate change mitigation, and bring in high precision analytics for such Earth systems modeling. And again, it is not too much away from material science, because this kind of Earth system modeling and remodeling is happening because of the indiscriminate use of certain materials which are not that great. Yeah. So you please be on the lookout, especially for faculty members at HBNI, for our calls in exponential technologies, which is really something where we are looking at exponential thoughts. We are looking at exponential research and exponential enterprise, where we can blend in your knowledge, where you can blend in your idea with translation and with the fusion of technologies to bring in a step that is away from normal, right? If you take normal steps, and I'm not going to read the quotation here, you take normal steps, but if you take exponential steps, you're going to really reach the destination quicker. And that is the whole idea of SCRB, to bring in exponential technologies to R&D laboratories and eventually to the doorstep of our population. We have technology translation awards. You can go through it. I won't go into the detail, where we are supporting patents which can be brought out as a technology or a translational product. So we are providing quite a bit of support. We are also interacting with quite a number of industries for new kind of materials for semiconductor chips, VLSI and AIML, and some of the industries that we have been able to bring into our fold is Intel, Applied Materials, and General Electrics. And so you can be sure of new calls that are going to come in near future. So please be on the lookout, do apply to us, and try to bring in your best ideas to us. So the final slide is that I have been able to tell you that, quite a bit of exciting initiatives are happening in science and technology research and development, including support for our young people, because we definitely need trained manpower. I am getting old. Everybody else is getting old. The future is sitting in the classroom, listening to advanced materials chemistry course. Once they are trained, once they are able to see the light or see the benefit of translation research, then and only then we are able to do cutting edge science. We'll be able to be future ready. And of course, quite a bit of other activities. I won't have the time to go in the detail, but our efforts are going to touch upon, policies, societal connect, tech incubators, accelerators, technology solutions, and lifelong learning opportunities. So all that is going to be bundled by SCRB and DST in one place. And hopefully we'll be able to sort of kickstart a new thought process and bring in the deliverables far quicker than what we have done in the past to the table, to the doorstep of our population. So with these with these words, I would like to conclude my talk. I would like to thank all of you for your very patient hearing. I think I took my half an hour which were allotted. I wish the very best to our student participants who are in the course. You have a great program. You have great mentors, and of course, HBNI is a remarkable institution. I wish you the best, and thank you very much, Professor Tyagi, again for this opportunity to be present and on this moment and talking to all colleagues in HBNI as well as student participants. Thank you very much. Back to you.
Thanks a lot, Professor Verma, for your wonderful lecture. Please be assured your all suggestions like blue sky research ideas, out-of-box thinking, and to identify some high-risk problems will definitely form part of this course. All teachers are sitting here, 3 of them are here. I will request them to find time to have this kind of discussion wherein some of your ideas can be implemented. And I'm pretty sure that your presentation will be very useful to faculty members and faculty members to be, those who are doing PhDs right now, they will find it very useful to get funds when they make their career in coming years. So thank you very much for kindly sparing time to be with us on this occasion. Now over to Dr. Anshu Singhal. I'm sorry.
I now request Dr. Dimple Datta to deliver vote of thanks.
Good evening, everyone. On behalf of the organizing body of this online course on Advanced Materials Chemistry, it's my privilege to propose a vote of thanks for this event to all the dignitaries and participants assembled here, both offline and online. I would like to thank by sincerely thanking our chief guest, Professor Sandeep Verma, who honored this occasion by sharing his thoughts on the gap areas in our understanding, which requires special effort in research, particularly in sectors of energy storage and conversion, and also water, climate, and geohazards. Thank you, sir, for your insight, deep insight into these different areas. I would like to express my gratitude to Professor Vasudev Rao, Vice Chancellor of Homi Bhabha National Institute, for his constant encouragement and support and the amount of effort he has put in conceptualization of this course. And his interest in this field is amply evident by the small speech which actually set the ball rolling. My sincere thanks to Professor P.D. Nayak, Dean, HBNI, for his encouragement and constant guidance to how to get this program, set and up and running. My sincere thanks to our course director, Professor A.K. Tyagi, Senior Professor, HBNI, and Associate Director, Chemistry Group, for his untiring efforts in shaping up of this course. Being one of the topmost material scientists in the country today, Professor Tyagi's insights into the content of the course material has enriched it immensely. His short introductory lecture today is a fitting prelude to the intriguing world of materials chemistry, which will be explored now in the course of 30 lectures. I would like to express our profound gratitude to Dr. J.P. Mittal and all other dignitaries from DAE and non-DAE institutes for honoring us with their presence in this inaugural session. Sincere thanks to Dr. Anshu Singhal, our course coordinator, for her exceptional organization skills, which smoothened the execution part of this program. We thank all the lecturers, the resource persons for taking time out of their busy schedule to conduct this course, and to all our participants whose enthusiasm for registering for it has made it a symbiotic process. Last but not the least, I'm happy to express a vote of thanks to all the staff members of HBNI who have worked tirelessly behind the scene to organize this event. Thank you, one and all, for your efforts in making this possible with your kind contribution.
So with this, the inauguration function is over. And all the participants, please join on Wednesday. There is a day on which first lecture will be taken by Dr. Vinita Grover Gupta. Professor Verma, let me thank you once again. And I hope to host you to HBNI in person in coming months.
Thank you so much. Thanks for having me.
Thank you, Professor Verma.
Thank you, sir.
We can close the program.
We disconnect now.